to be perfectly quiet and paying attention and writing everything I do or say. Are you ready? Okay. So we did a couple of examples last time, and let's take this one, the ideal gas law, and let's do two specific problems coming soon to a 1045 lab near you. There are a couple of things that you can do with the ideal gas law. You can actually find a molecular weight. This is one of your experiments. This is experiment number 9 in the 1045 lab. And here's one other thing that you can do. You can actually find density. You can. It's really cool. You are going to take an unknown in experiment number 9, and you're going to put it in a Florence flask. And you're going to trap it as a gas in a Florence flask. So inside of this container, you're going to have a fixed amount of substance trapped as a gas. And we talked about this. Gas particles will occupy the full volume that they're given, and they exert pressure by crashing into each other and the walls of the container and bouncing around in straight lines. That's how gases exert pressure. But here's the thing. Suppose that you have the grams of the gas, which is what your experiment is about. You guys are going to actually measure. You're going to trap a gas and measure the weight of a gas. So suppose that you have grams of a gas, and you can have volume of the gas, and you can have pressure of the gas, and you have temperature of the gas. All of these are measured quantities. How do you measure a volume? Well, you get a graduated cylinder. It's part of the experiment. How do you measure a pressure? There's a barometer in the room. You guys are going to measure atmospheric pressure. And the temperature, you've got a thermometer. So every single one of these can be measured. And if you have all that, look what you got. You got the pressure, the volume, and the temperature of the gas. Check, check, and check. If you also have the grams of the gas, look what happens. Pressure of the gas times volume of the gas equals the grams of the gas divided by the molecular weight of the gas. R is what? What's R called? The ideal gas constant. And what are the two values for R?
62.4
and?
Or 0.0821.
62.4 and 0.0821. And if you have the temperature of the gas. Look, all of this is known. The pressure, the volume, the mass, that's a constant, and the temperature. Which is the only thing you don't know? Yeah, exactly. And that's your X. That's exactly right. Let's write up a problem. Let's write up a problem. A sample of a gaseous hydrocarbon was trapped at 759.3 torr and 95.5 degrees centigrade in a flask of 495 milliliters. In fact, make it a little smaller. Make it 240 milliliters. Find the molecular weight of the gas. Sample of a gaseous hydrocarbon was trapped at 759 torr and 95.5 degrees centigrade in a flask of 240 ml. Find the molecular weight of the gas. Find the molecular weight of the gas. So, apparently, this is you taking a container, a flask, that the volume equals 240 milliliters. As soon as I trap a gas inside a container, that's the volume of my gas. Because what? Because gases trapped inside of flasks occupy the full volume. It's what they do. They bounce around inside, crashing into each other and the side of the container. However many grams the sample weighed, that's the weight of your gas. The sample weighed 0.850 grams. Can you give me an example of how, now that you've been in the lab a while, you've half a semester of chemistry lab, right? So you're familiar with your surroundings. Can you tell me how that's going to go down? How are you going to tell me the grams of the gas? Just curious. Okay.
You can measure the flask.
Hmm?
You can measure the weight of the flask. Then zero the weight and just add the gas.
Pump. How do I add a gas?
Stop it.
Okay. By putting a stopper on it and on it. Okay. So tell me again that subtraction that's going to give me the grams of the gas?
You know, weigh the flask and zero the weight and then add
Just the flask one? Oh, the flask and the stopper. Okay. So this is going to be flask plus stopper. Okay, got it. Now what?
Now you zero the weight and then add the gas.
I'm getting lost in the adding the gas thing. Because here's the gas. And I don't know how to add a gas. Although I like the subtraction idea. I like that. So suppose that you had the weight of the flask and the stopper. At the end of the experiment, what can you really measure? The flask, the stopper, because otherwise the gas is going to get out. And somehow you have the gas in there. Is that correct? Okay? Okay, so tell me, how do I get the sample of the gas? How did the person get those 850? By subtracting, get rid of the flask and the stopper. And this should give me grams of gas. I agree with you. I bet you that that's how this person did that. By the way, I hope you know that that's actually not possible to measure. How are you planning on measuring just the stopper and the flask? No, tell me. How are you gonna do the stopper and the flask? What about if they were clean at the beginning of the experiment, before we put the gas in it?
They'd have to be a factor.
Huh?
The stopper and flask have oxygen in them? That's what you're saying?
Yeah.
So it'd have to
What's
be a
inside?
factor.
What's inside of everything? What's here?
Air.
Don't say nothing, because I know it's something. So you know. And this point right here is the subject. That point right there is the subject of an adjustment. In the labs, in your labs, a lot of the conversation is going to be about eliminating the moist air from the flask. That cannot be done. In fact, it can only be done on paper. And part of your calculations for experiment number 9 will be how to remove the moist air from the calculation so that you can go ahead and do this. So you can actually get those grams. Your lab teachers are going to spend a lot of time talking about this. This point is on lab exams, on the CHEM1045 lab exams, on the 3rd lab exam. That point, exactly the way I'm talking about it and exactly the way your lab teachers are gonna talk about it is on the lab exams. So I'm telling you now, so a red flag goes up. That, oh, wait a second, there's gonna be something weird about the calculations of the grams of the gas. Heads up for the lab. So, if I have everything, according to the problem that I set up, if I have everything, it turns into, plug in the numbers. Isn't that right? Okay, help me out. How do you do it? Go.
75.
What's the pressure?
75.3.
759.3, and this is units of? Torr. What was the volume of the flask? Huh? 0.240 liters equals 0.850 grams divided by the only thing I don't know, which is my x. The only thing I don't know, which is my x. And what R are you going to use?
62.1.
And why are you going to use that?
Torr.
Because it's in torque. And what do you got? What are you going to put? What do I put? 62.4 and torque. And the temperature?
Yeah, making it cover.
I'm waiting. I can't wait. Go for it. Just, 3 minus 5. What? Let's think about this for a moment, and believe me, today I'm going to be a witch and a half, or something that rhymes with witch. Are you seriously telling me that it's taking you longer than 5 seconds to add 273 to a number? We gotta take a deep breath and do a lot of self-examination. You gotta take a long look in the mirror. How much is it? 368. Did I make it a point something? Okay, 0.5. How long is it going to take you to solve for x in a denominator? Molecular weight equals. You're already taking too long.
0.107.
Got it. Where's your calculator? Everybody needs to do this. The molecular weight is in the denominator, right? Okay. And to solve for x, x has to be alone. It can't have any coefficients. It has to be positive, and it has to be on top. And right now, that x is on the bottom. How much? 107.3. And this, what are the units of molecular weight? Grams per mole. Did everybody get the same answer? Okay. Molecular weights in the decimals are not possible. Molecular weights in the decimals are not possible. How many people got this answer? Everybody? Okay. Everybody needs to be doing work and getting the same answers. So, molecular weight. Molecular weight of a gaseous compound is actually a historic experiment. It's one of the earliest things that people did with gas measurements. The other thing is a density. Look at this statement. Find the density of oxygen at STP. Look at that. Find the density of oxygen at STP. That sounds like a very short set of instructions. The density of oxygen at STP. Density, what's that? That's mass over volume, right? where do I see density in PV equals nRT? It's in grams over volume, right? Yeah? Yeah, look, PV equals nRNT. So PV equals grams divided by molecular weight R and T. Isn't that right?
Yeah.
So where's that density? There's grams and there's volume. So in order for me to have a density, in what unit specifically is it going to come out of PV or D? Grams per liter. Yeah, grams per liter. So for me to have this volume down here and preserve the grams in the numerator, what has to happen to everything else? So the P stays where it's at, right?
Yeah.
And now, molecular weight divided by R and T. There you go, density. Density from PV equals nRT. And they did say oxygen, and they did say at STP, is that correct? They did say oxygen, and they did say at STP. So do I have everything to find it? Do I have everything? What's P? If it's STP, what does that mean? 1 atmosphere or 760 torr? Which one do you want to do? Does it make any difference? No. Some people like using atmospheres because you get to put a 1 instead of 760. Do it in atmospheres. Look, 1 atmosphere is going to be, what's the molecular weight of oxygen? 32, right? Okay, just checking. And if you use 1 atmosphere, you got to use for R what? 0.0821. And what was the temperature? STP, what's the temperature? STP, what's the temperature? 0 degrees centigrade or 273. And there you go. This is your density at STP for oxygen. Did you notice? In grams per liter. Did you notice that molecular weight is directly proportional to density? Did you notice? That molecular weight is directly proportional to density. Did you notice that? Yeah. Does that make sense? Does that make sense? Oh, absolutely, it makes sense. It totally makes sense because if I'm always talking about a gas inside of a fixed container, the density of oxygen at STP, what if my particles weigh more? Then what happens to the density? The density gets higher because density is mass over volume. And if my particles actually weigh more, of course I'm going to have a higher density. So absolutely, I agree that molecular weight is directly proportional to density when it comes to ideal gases. Is that fair? Is that okay? Any questions? Yeah, please.
Where'd you get the 0.0821?
I memorized it. It's one of the 2 constants for R. What's the other one? 62.4. What is it in atmospheres? 0.0821. Was it in torr? 62.4. Everybody okay? Any questions on how to do molecular weight or density? You good? Okay. Here's something. Yeah, tell me. Anybody? Tell me.
Scared to ask, but you said you can't have a
What's the worst that can happen?
You can't have a decimal point for the grams per mole. So what do we do with that?
Right.
Last that 3.
No, the decimal. I heard somebody say that the answer to the problem was 0 point something.
Okay.
That's not possible for a molecular weight. Because the smallest molecular weight we can possibly have is what? In terms of a gas? 2, because hydrogen's diatomic. So you can't have molecular weight 0 point anything. Now, can it be rounded off? Yeah, I mean, the decimal means that you can't have anything less than 1. You can't. It's not possible. That just usually
But
means you did something creative with the math.
I was just curious, in that case, we could round off at 3?
Yeah, but the important part here is that this number is higher than 1.
Okay.
That's what I meant by decimal. You
Okay.
can't have decimal, molecular weights that don't make any sense. Yeah, tell me.
My other question is, why did you change the temperature from 0 degrees centigrade to Kelvin?
Because the units of R is atmosphere liter over Kelvin moles. You have it from last class notes.
Yeah, it's the same thing for the above.
The units of R. Remember we talked about it?
Yeah.
About the units of R? Everybody okay? So temperature units, pressure units, and volume units all have to be internally consistent. So if you're working in torus, you gotta use 62.4. If you're working in atmosphere, you gotta do 0.0821. And everything is in liters. Okay? Is that it? Okay. Let's talk about this one. Let's talk about this other type of problem. That type of problem is going to be, just like we did last class, is going to be 2 sets of conditions. Hey, what happens to the volume of a gas if I change these conditions? That means you're going to use a combined gas law. Are we clear on that? That's from last class. Is that right?
Yeah.
If they talk about a single set of conditions, it's P equals nRT. Is that good? Look at this special problem. Listen to this. What happens to the volume of a gas if you triple the temperature and decrease the pressure to 1/3 of the original? Does it look like they're giving you any information? Nope. Not at all. I don't have an initial set of conditions. I don't have a second set of conditions. They're giving me no numbers whatsoever. But I can tell, however, that it is what kind of a problem. Is it an ideal gas law or a combined gas law? It sounds like they're changing the conditions. Is that correct? Okay. 1/3 of original. These items, this one, and this one, can be anything. And some of them are easier to answer than others. We good? Some of these you can work out in your head like Kevin did. Some other ones you can't. But it sounds like there's no numbers to put in. And there actually are numbers I can put in. Anytime you get this, and these are very popular, twists to P1 V1 over T1 equals P2 V2 over T2, that are extremely popular in the GRE, and the MCAT, and the PCAT. And this is what you're going to do. You're actually going to work it out as an exercise. You actually have numbers you can use. You're going to set it up. The first thing, what's my X? Which one, V1 or V2? V2. Because the question of what happens to the volume of a gas obviously is under the second set of conditions, because I'm going to change them somehow. So right away, my X is V2. We good? Okay, solve for V2 for me. V2 equals? Well, damn the remedial math. Well, what's the math prerequisite that goes along with this class? What's the math prerequisite? It's Mac 1105. If you guys are still hung up on algebra, it's gonna be a lot of pain, What goes down here? P2, right? Is that right? Okay. So now,
What about
and what about T1? Where's T1? It stays up there. That never changed. I never changed that one. And now, I'm actually going to put numbers up there. Did they change the temperature? Did they change the temperature?
Yes.
Okay. I'm just checking. So I actually have numbers to put up because I may absolutely not know what P1 was, but I sure know what P2 was. What was P2?
P1.
P1 divided by 3. Exactly. P2, this one right here, what was it? 1/3 of original. So isn't that P1 divided by 3, or 0.33 P1?
Yep.
Isn't that true? I absolutely have no idea what V1 was. V2 is my X. Got P2, I have no idea what T1 was, no clue. But I know what T2 is. What is it? 3 P 3 T1. Is that right? Where did you get that information? Those are the two things they're going to say. And now? Oh, look, that's gone. Oh, look, that's gone. So tell me, what happens to the volume of a gas? What happens to the volume of a gas when you triple the temperature and cut the pressure to 1/3 of the original? How much is 3 divided by 0.3? If you're unsure, grab the calculator. Although that's a scary thought, but okay. 3 divided by 0.3, and that is 9 V1. What happens to the volume of a gas when I cut the pressure to 1/3 of the original and triple the temperature? It goes to what? 9 times as much. So you can answer the problem, and all you have to do is put in the correct numbers. You want to try it again? Try it. That's giving me the problem. They told me that they cut P to 1/3 of the original.
Oh my god.
So the second pressure was 1/3 of the original. Try it again. What happens to the volume of a gas?
Ya tenemos 3, ya no podemos acabar ahí. Dale, muchacha. ¿Para qué tanto? Bueno, 2 más.
If you have the pressure at constant temperature, what happens to the volume of a gas if you have the pressure at constant temperature? Don't forget the first step. Which kind of problem is this? A PD equals nRT with a single set of conditions, or is it a manipulation of conditions? What is it? A manipulation of conditions, where they have a first set of conditions, they change something, and then they have a second set of conditions. Which one is it? It sounds like they're changing conditions. So that's a P1 V1 over T1 equals P2 V2 over T2, a combined gas law. Right? And then you write it out, combined gas law. P1 V1 over T1 equals P2 V2 over T2. What do I do with this piece of information? What do I do with this piece of information? You know what? I actually forgot to tell myself. If it's constant temperature, what do I do with the temperature? What do I do with the heat? Get it out of there. What are you going to divide both by the same number? What for? You don't even have it. If it's constant, get it out of there. Great. Don't even put it in there. Cancel it. What's your X?
V2.
Always V2. What happens to the volume of a gas? So solve for V2 for me. V1 stays there, and V2 comes down here. Okay? I have no idea what P1 was or what V1 was, and V2 is my X. But I do know what P2 is. P1 over 2, 1/2 of P1, isn't that right? Because that's what they said they were going to do. They said they were going to do what? Cut the pressure in half. So P2 is going to be what? 0.5 of what? Of P1 equals V2. And now we're in the same boat we were a minute ago. P1 cancels. And V2 equals to? V2 equals? Dividing by half is the same as? So what happens to the pressure of a gas? When a constant temperature, you cut the pressure in half. You double the volume. So you can answer them, but you got to be doing it in an organized fashion. The first order of business is to recognize the problem as a combined gas law problem. Then the second thing is put in the letters correctly. If the question is what happens to the volume of a gas, V2 is your X. Any questions? You sure?
How do you know it's happening?
Yeah.
Half the pressure.
Because it says it.
Let's say how.
Oh. Yeah. Cut something in half.
Half. Antes lo tengo ahí. Half. Pero no lo estoy usando.
H-A-L-V-E. H-A-L-V-E.
Ahora dije. Okay.
Alright, next. Tell me, what's up? Shh, guys, feed a calorie. Pipe down. How do you know which one? What do you mean by operation? Or P equals NRT, by the sound of the problem. And as soon as you do about 75 of each kind, about 2 or 3 times, you think I'm joking, I can tell. And as soon as you do 75 of each kind, several times over, you too will also have no doubt whatsoever. Because by doing dozens of problems several times on the day that you took the class, that means today. And looking up new words in the dictionary, is worst case scenario is that you have a very false sense of security because you kind of get something. Because you're going to kind of get a D. That's what happens every semester. The beauty of it is that you do get it. Look, 1045 is an adjustment period. You guys are right now, and this happens every October, it happens every March. Right now, you're running around chasing your tail. For the second exam, you studied a little bit more than for the first, if at all. And then you said to yourself, so, I'm going to do better on this test. You are on your way to learning. Ah yes, my young Padawans. The problem here is that you have no idea, zero, most of you, I don't want to generalize, most of you have zero idea of what it is to study hard. None whatsoever. The thing is that you guys are wonderful, you're young, and you can adjust. Once you get older, it's harder. But it's true. But you can adjust. There's hope for you guys. But you've got to trust me. Your nomenclature, there were some good entries into my list. I will not be so tasteless as to tell you what they are. I can share with you some ones from past semesters. But the fact that you did so horribly in nomenclature tells me the story of how you guys studied for the test. You cannot study 3 days before a chemistry test. Not even if you spent 5 hours at FIU or at Starbucks. Really? 5 hours? Tell me more. 5 hours? After 5 hours of studying, sometimes I don't understand stuff. After 5 hours is when I begin to see what it is that I don't understand. And that's where you guys are, I could tell. That you guys are about to figure out what hard studying means. How many people are going to med school? Be right. Go ahead. How many people want to go to pharmacy school? Yeah? And it all starts here. This is where you learn to study. And what you're doing now is not it. We got to get a different plan. So, molecular weight, densities, the cutesy little problem that they look like they don't give you any information. And one last thing before we stop. The molar volume of a gas. FYI, gas is chapter 12. FYI, gas is chapter 12. I'll be done on Friday. The gases are completely finished on Friday. Electronic distribution is next. Did you guys get my list of topics for the final?
Yes.
Have you mentally begun to check them off? The molar volume of a gas. The molar volume of a gas. 1 mole of any gas at STP occupies a volume of 22.4 liters. 1 mole of any gas at STP equals 22.4 liters. The most amazing thing. That falls right out of Avogadro's law. It is the most amazing thing. It is a unifying feature, property of gases, that no matter what gas it is we're talking about, whether it's helium, hydrogen, water, or gas gold, where I can fix the temperature and the pressure so I can have gas gold, it's totally possible. All of these behaviors are the same if one assumes ideal gas behavior when it comes to pressure, temperature, and volume of a gas. Okay? Okay, sorry. 22.4. And let's play a little game. If I tell you that I have 22.4 liters of a gas at STP, how many moles of a gas do I have? 1. How about if I had 11.2 liters of a gas at STP? How many moles do I have?
You have half a mole.
0.5 moles, right?
Yes.
Yeah. How about this? How about if I have 44.8 liters of a gas at STP?
2 moles.
2 moles, right? Right? Okay. How about this? How about if I had 2.24 liters of a gas at STP? 0.1 what? Good. How about 4.48 liters of a gas at STP?
0.2 moles.
Beautiful. From now on, people writing problems will fool you by, instead of telling you the number of moles of a gas that they have, they'll give you suspicious multiples of 22.4 and tell you that that's how much they're holding at STP. And now you too know how to know how many moles that is. Because any gas at STP occupies how much? 22.4. And that number is almost as famous as 6.02 times 10 to the 23rd. That's the molar volume of a gas at STP. Is that fair? Okay.